We'll begin with discussion of some basic design techniques for algorithms. We'll start with fairly simple problems that many of which you may have seen, but soon we'll hopefully see solutions to non-trivial problems which you may not have seen. The first example I would like to start with is finding the minimum element in an array. Okay, so the input problem is find min. Okay, the input is an array A, and the output is a minimum element in A. Okay, an element with whose value is the minimum. Okay, this is a problem which most of you would have seen earlier in your perhaps the first programming course, maybe later even in your course on data structures. Okay, let's anyway go over this solution. Okay, so the standard solution is you take a temporary variable. Okay, there's a temporary variable which contains the current minimum. So this contains the current minimum and it's updated at each step. So you start with the first element in the array, okay, and then you scan the array element by element, the first element, then the second element, third element, and so on up to the last element in the array. Each time you compare the array element with temp and update temp if necessary. Okay, this simple technique actually is very powerful and used often, which is if your input is in the form of an array or a list, then if you can solve the problem for the first n-1 elements of the array, can you solve it for the nth element? Okay, this is the step which is put in a loop. So let me just write this down. So the important step is this: if AI is less than temp, then temp is set to AI. Okay, this is the crucial step, and this is usually put in a loop. Okay, I varies from 1 through n, where let's say n is the size of the array, and at the end of this, temp will have the minimum element in the array. So I will be, when I discuss algorithms, often I may not write the full code. In fact, I will not write the full code. The idea is to give you the main ideas behind the design of this algorithm. I may not take care of some of the stray cases. Okay, I may not initialize variables properly, etc., etc. So all these programming details I will not get into. Okay, the main idea is to get the the techniques and the ideas behind the algorithm which solves the problem, and you should be able to sort of take these ideas together and write a program which actually works. Okay. Yes. So if you look at this, this is the level at which we will describe algorithms, maybe even less. Okay, I could just say scan the array element by element and update the current minimum as required. Okay. Okay, there are two things, couple of things that I would like to point out. So this thing, this design technique is often called, well, induction. Both recursion and iteration actually go with this. I'll explain this a bit more. The second technique, the second sort of thing we'll keep in mind is ordering. Okay, and the third thing is to store values already computed. I must add store necessary values. Okay, so let's go over each of these one by one. So induction, what I mean by induction is this: you want to solve a problem. Okay, your input has some size. Okay, the array has say size n. Now the one way to solve it is, supposing you can solve this problem for smaller values of input. Okay, if this problem can be solved for smaller values of input, now can I extend these solutions to a solution for the bigger input? Okay, if you can solve the problem for smaller values of the input, can you extend the solution to a bigger value of input? For instance, if I can solve a problem for all arrays of size n minus 1, can I solve this problem for an array of size n? Now this step, which takes you from n minus 1 to n, is often is the crucial step, and once you come up with this step, you just put this step in a loop, or you use recursion. Okay, you first recurse on an array of size n minus 1 and then extend it to an array of size n, or you scan the array one by one, element by element, and you update the solution as you go along. So this is what I mean by induction, and it is at the base of every algorithm design technique. Okay, you can call it the mother of all algorithm design techniques. You will learn some more fancier things later, but this is the very crux of the design of every algorithm. Second point that I would like to make is ordering the input. Okay, looking at the input in the right order often helps. In this case, it's simple. You know, you look at the array elements in increasing order of the array index. Okay, in fact, you could look at the array in any order. It really doesn't matter. But there are cases, we'll see cases where ordering plays a very crucial role, okay, in solving the problem. The third thing, which is also fairly simple here, is to store some of the values that you've already computed. Okay, that's the third point I want to make. Now, even in this case, it's simple. You just store the previous minimum. Okay, the variable temp, the temporary variable which we had. So these are values that you would like to use in future. Okay, almost every algorithm design technique that we'll study are a combination of these three. Okay, some of them will use just induction and storing old values. Some of them will use all three. Some of them will just order the input and use induction. Okay, so these three are things that you must keep at the back of your mind when you design any algorithm. Let us analyze this algorithm. So here's an analysis. Every algorithm that we design, we will analyze. Okay, analysis is as important a part of this subject as design is. Okay, and we would like algorithms to be as fast as possible in the worst case. So all our analysis pertain to worst case, and we would like to design algorithms which are as fast as possible. Okay, so in this case, we look at every array element once, right? And we make one comparison per array element. This leads to, so we make n minus 1 comparisons. We don't really compare anything with the first element, but with each of the subsequent elements, we make one comparison. N is the size of the array. Okay, so we make n minus 1 comparisons. Along with comparisons, okay, we need to, we also store this new value in temp, right? But the number of times we do this exactly equals the number of, I mean, it is, let's let's say 1 more than the number of comparisons we make. So if you're not really worried about constants, then we can just focus on the number of comparisons. As long as I can bound the number of comparisons, the other small operations that I do, like incrementing the index variable of the array or storing the value in temp, they all are of the same order as the number of comparisons. Okay. So the time taken here we would say is order n. Okay, the time taken is order n, but our focus is just on the number of comparisons. Okay, I think a question that one can ask and one should ask is this the best? Can I find the minimum element in an array in using less than n minus 1 comparisons? Well, if you just think about it, or even if you don't think about it, I guess most of you will jump up and say, of course you need n minus 1 comparisons, right? That's the sort of first reaction that most people will have, that without making n minus 1 comparisons, how can I find the minimum element? Why is this so? Can you logically argue that you actually need n minus 1 and you can't do with less than n minus 1? This argument is easy but not absolutely trivial. Okay, let's see. So why should we make n minus 1? Can we do it with less? Well, every element you have to look at least, right? Every element in the array must be compared to something or the other. If it's not compared, okay, then you may actually make it the minimum, right? It could be the minimum. If you had output something else as the minimum, then this could have been made the minimum. Or you can easily make some other element of the array the minimum. Okay, so without comparing, if you do not compare an element, then you cannot tell the minimum element in an array. Now this gives you, this doesn't give you n minus 1, it gives you n by 2. Okay, assuming n is even, so at least n by 2 comparisons are needed. Okay, the reason, every element must be compared, must be in some comparison. Okay, what I mean is every element must be compared with some other element. Okay, this can be done with n by 2, by the way. Okay, so the first element is compared with the second element, the third element is compared with the fourth element, okay, and so on. The fifth element is compared with the sixth element, and so on. So with n by 2 comparisons, if n is even, or n by 2 plus 1 if n is odd, well, ceiling of n by 2 comparisons are all that's necessary to sort of satisfy this condition that every element must be in some comparison. Now clearly n by 2 is not the right answer, n minus 1 is the right answer, and why is it that one needs n minus 1? So here is an argument. See, initially when you have not made any comparison, there are n candidates for the minimum, right? Each element in the array can actually be a minimum, right? You don't know which of these n elements are a minimum. Now when you make a comparison, you can get rid of only one of these candidates, right? When you compare, let's say at some stage you have candidates x1, x2 up to xk. Okay, some k elements are candidates for the minimum. Each of them, based on the comparisons that you have made previously, each of them is equally likely. I mean, each of them can be a minimum. Okay. Now, if you compare two of these candidates, you can get rid of one, right? Whichever one is smaller, that still remains a candidate. Whichever one was larger, that no longer remains a candidate. But you can only get rid of one candidate. So with each comparison, I can only get rid of one candidate, right? I have n candidates to start with, so I need n minus 1 comparisons. Okay, this is a Okay, this is actually a complete proof, though a bit hand wavy. You can make it more more rigorous also. Here's one more way of looking at it. Okay, supposing you draw the following graph. So initially I have all these nodes, let's say the elements x1, x2 up to xn. These are elements in the array and also vertices in our graph. Okay, so let me just put a circle around these to indicate that these are also vertices. Now when you compare xi and xj, okay, here is xi and here is xj, I draw an edge between these two. Okay. Now when you compare, let's say, x1 and x2 and xn, I draw this edge. Now if xj and xn are compared, I draw this edge, and so on. As you make comparisons, I keep drawing these edges. Okay. Yeah. So once your program ends, terminates, you've done all these comparisons. Now I look at this graph and I look at each connected component in this graph. If there are more than one connected components in this graph, then I will not be able to tell the minimum. Okay. Now in each connected component I know which is the minimum. Okay, there will be one which is the minimum, but I can surely give values to these so that I can pick the global minimum from any one of these connected components. Okay, so here this is an argument that after the comparisons are over, okay, once you finished all comparisons, I better have one connected component. This means from your discrete structures class, you know that you need n minus 1 edges. Okay, good. So this is just the same argument. Both of them have it's the same idea behind both. For instance, here you start with n connected components, and each time you add an edge, you can decrease the number of connected components by 1, at most 1. Okay, so it's the same argument. Okay, so you need n minus 1, and this sort of simple scan of the array does it with n minus 1 comparisons. Okay, let's look at a slight variation of this problem. Now I want to find not just the minimum in the array, but also the maximum. Okay, so this problem is called maxmin. Okay, so the input is an array A, okay, and the output is the maximum and minimum elements in A. Okay, so I want both the maximum and the minimum element in A. Now if I just wanted to find the maximum, the procedure is clearly the same as the one for the minimum element. Okay, what if I want to find both the maximum and minimum? Well, I could first find the minimum and then I can find the maximum. How many comparisons does this take? Well, n minus 1 for the maximum, n minus 1 for the minimum, and that makes it 2n minus 2. Right? So the number of comparisons that the naive algorithm, so this is the number of comparisons that a naive algorithm makes. We can ask the same question, is this the best? You can try the previous argument that we had of connected components, and so you can show that you need n minus 1. Okay, that's fine, but anything more than that is very difficult to prove. Okay, well, it's not absolutely impossible, but it's difficult, and if you try to certainly increase it to 2n minus 2, it's impossible. Okay, you will not be able to prove it. Okay, so let's look at some small values. Supposing I have 4 elements. Okay, I have, let's say, x1, x2, x3, and x4. The naive algorithm took x1, compared it with all of them. Okay, found the minimum, and then we were done. Then we took x1, we compared it with all of them, and while maintaining the maximum, okay, the temporary maximum. Now many of these comparisons are repeated, right? So you will see that some of these comparisons that you make when you unroll the whole thing out are repeated. So our aim is to sort of get rid of these unnecessary comparisons. Okay. Now in 4 elements, here's what you can do. I first compare x1 and x2. Okay. So supposing x1 is less than x2. So this is the first comparison. Okay, x1 is less than x2. Now I compare x3 and x4. Supposing x3 is greater than x4. This is my second comparison. Okay. Now where do I find the minimum? I mean, how do I find the minimum? The minimum clearly is either x1 or x4. Okay, it's the smaller of x1 or x4. So I compare these two and find the minimum. Right. Similarly, I compare these two and find the maximum. Good. So how many comparisons have I made? I have made 1, 2, 3 and 4. So 4 comparisons. Now what does our old algorithm say? It says 2n minus 2, n is 4, so this is 6 when n is 4, right? So we seem to have done certainly better than 2n minus 2. When there are 4 elements, we have certainly done better than 2n minus 2. And well, the trick was, once we found the minimum and maximum between x1, x2 and x3, x4, then for the minimums, right, I only need to look at x1 and x4. Okay, the smaller on the left hand side and the smaller on the right hand side. I don't have to bother about the bigger ones. And similarly for the maximum. So this trick, can we apply recursively? Well, it's certainly worth trying, and let's do it. Okay, so what we do is this. Here's the, let's say you have an array of size n, right? So let's divide this into 2 parts. Okay, recursively find the maximum in this part. Let's say max L. This is the left part and that's the right part, and min L. Recursively find the maximum and minimum on the right hand side. So that is max R and min R. Okay. Now how do I find the maximum and minimum? Well, I need to compare these two to find the minimum. I need to compare those two to find the maximum. Okay, so here's an algorithm that seems natural. I divide this into 2 parts. Okay, divide this into 2 parts. Let's say 2 equal parts, 2 equal halves. Halves are always equal. Okay, I find the maximum and minimum on the left hand side. On the left half, I find the maximum and minimum on the right hand side. Now I compare the 2 minimums to output the minimum of the array. I compare the 2 maximums to find the maximum of the array. How many comparisons does this algorithm take? Okay, let me write down the algorithm, but in future with this explanation you should be able to write the algorithm, right? So divide into halves, let's say left and right. Okay, then recurs on both parts. Okay, on the left and the right, and the answers are maxL and minL and maxR and minR. Then put these things together to get the minimum and maximum. Okay, and then compute final solution from the solution of the 2 parts. Well, I have written the essence of the algorithm without really writing details, and I hope you can fill in the details, right? Okay, define procedures and write down recursive calls and do these two comparisons and output the minimum maximum. Okay. Okay, so how many comparisons does this take? Okay, that's the question we need to answer. So let's say Tn is the time taken by max-min on arrays of size n. Okay, it's the time taken by max-min on arrays of size n. Then Tn is, there are two problems of half the size. You solve two problems of half the size, that is 2n by 2. Okay, okay, plus two more comparisons, one between the two maxes to get the new max, one between the two mins to get the new minimum. Okay, so this is for the recursive call. Okay, you call the left hand side, that's n by 2, right hand side n by 2, and then 2. Well, if n is odd, I would have a ceiling and floor somewhere, but let's not worry about it for the time being. Okay, let's assume that n is even. You can assume n is a power of 2 if you want. Okay, we also know that T2 is 1. Okay, if I have two elements, I can find it in one comparison. So what's the solution to this recurrence? Let's see. So the easiest way to solve all this is to check how this recurrence behaves. So Tn is nothing but 2, and now I open this out. This is 2T n by 4 plus 2 plus 2, okay, which is 2 squared T n by 2 squared, okay, plus 2 squared plus 2. Right, you can write this down once more, and essentially we want to see how what pattern this follows. Well, it's not too difficult to guess what the pattern is. The pattern is this. So Tn is 2 to the I, right, Tn by 2 to the I plus 2 to the I plus 2 to the I minus 1, and so on all the way up to 2. Okay. So now we set n by 2 to the I to be 2, because we know that T of 2 is 1. Okay, then we have T of n is 2 to the I, right. This becomes 2, so T of 2 is 1, okay, plus 2 to the I plus 2 to the I minus 1, and so on up to 2. Okay, so this is nothing but 2 to the I plus 1 plus, well, 2 to the I minus 1, and so on up to 2. Okay, you can check that this is nothing but, we also know that 2 to the I plus 1 is n, and I hope you can solve this. Okay, I will leave it for you to solve this. This is nothing but n, and this sum you will get as n by 2 minus 2, right. If you sum this up using the usual geometric series and use this fact that n is 2 to the I plus 1, you will get that this sum is nothing but n by 2 minus 2. Well, put this together, you get T of n is 3n by 2 minus 2. Okay, you can check that this, when n is 2, this is 1, which is what we want, and this also satisfies the recurrence that we had. Okay, the recurrence was, let me refresh your memory. The recurrence was Tn is twice Tn by 2 plus 2. So if I put Tn equals 3n by 2 minus 2, this satisfies the recurrence. You can prove that Tn is this by induction. Okay. Well, so the number of comparisons that we seem to make using this method is 3n by 2 minus 2, which is certainly better than 2n minus 2. Okay, we seem to have done something fairly mechanically, and we seem to have improved the number of comparisons made quite drastically. Okay, so this technique is is called divide and conquer. It was used by the British the last century, last century and even before that. Okay. We will put it to good use in designing algorithms. So let me write down the main steps of this technique. The first step is to divide the problem into, okay, I'll say 2 parts. Okay. Often we will want these parts to have equal sizes. Okay. Often of equal sizes. Okay. The next step is recurse on each part. Okay, so you recurse on each part and solve each of them, both the parts if there are 2. Okay, and the final step is put these solutions together. Put these solutions together to get a solution for the original problem. Okay, often you can just do this blindly. In fact, for the maxmin, we could have done it blindly. Okay, take this array of size n, divide this array into 2 arrays of size n by 2. Okay, find the maximum and minimum on the left array, the maximum and minimum on the right array, and once you have these 2 solutions together, now you find the maximum of the whole array by comparing the 2 maximums, find the minimum of the array by comparing the 2 minimums. Okay. Again, the essence is this induction. Okay, in the sense that if you could solve problems of smaller size, which is what you're doing in this recursion, you're somehow putting these together to get a solution for the big problem. Okay, how you find these smaller problems varies from problem to problem. Okay, let's look at another problem where we'll apply this method blindly and we'll see what we get. Okay, so this problem is to find both the minimum and second minimum. Okay, the minimum is the smallest element in the array, the second minimum is the next one. Okay, the second smallest element in the array. So your input is an array and you want to find both the minimum and the second minimum. The usual way you would do it is you first scan the array and find the minimum, right? Now you again scan the array and find the second minimum. The other way to do it is to have 2 temporary variables, okay, temp1 and temp2. In temporary 1 I store the current minimum, in temporary 2 I store the current second minimum. Now when I get to an array element I, let's say the ith element, I compare this first with the minimum, then with the second minimum that I have, and based on the result of these 2 comparisons I update minimum and second minimum. Okay. Now this will take, we've seen how many comparisons this will take. It is 2 n minus 2, okay, as it was in the max-min case. And let's just apply our divide and conquer paradigm blindly to this problem and see what we get. Okay. So how would we do this? So here's the array. The array is of size n. I divide this equally into 2 parts. Okay. I find the minimum and second minimum here. So let's say min left and the second min left, min right, and S min right. Okay, so I found these 4 values and now I want to find the minimum and second minimum for the entire array. The minimum is not a problem. Okay, so I just compare min and L, these 2 values, right, and I can output the minimum. The smaller of these 2 is the minimum. Now what do I do about the second minimum? Okay, now supposing min L were smaller than min R. Okay, so without loss of generality, this min L, so assume min L were less than min R. which means at this point min L has been outputted. Okay. Now what are the candidates for the second minimum? Clearly min R is still a candidate for the second minimum. Okay. Second minimum of the left hand side, S min L, is also a candidate for the second minimum. But one of these elements we have sort of thrown out, which is S min R. This does not figure in the picture at all. So we need exactly one more comparison to get the second minimum, which is, supposing this is true, then compare the second minimum from the left and the minimum from the right. Okay. So you need to compare just these two elements, and you can see that the minimum of these two will give me the second minimum, right. The minimum of the entire array I get by comparing these two minimums. Okay, the minimum, the left hand side minimum, the right hand side minimum, and the second minimum I can get by comparing the minimum element which lost the first comparison, which was larger, and the second minimum of the element that won. Okay, so that will give me the second minimum. Good. So how many comparisons does this take? Okay. Well, if you write down the recurrence, this seems to be very similar to the previous one. So what is, so if Tn is the time taken by the algorithm, we have two sub problems, each of size n by 2. Okay, that takes time T of n by 2, and then we have two more comparisons, one with the two minimums and one to find the second minimum. Okay, we also know that T of 2 is 1. If I have two elements, one comparison suffices to find both the minimum and second minimum. And these set of equations are exactly the same as the set of equations we had before. So the solution is Tn is 3n by 2 minus 2. So the number of comparisons we make is 3/2 n minus 2, and it's not 2n minus 2. Okay, it's much less. One can ask, is this the best? Can we do better than 3/2 n minus 2? This question can be asked both for max min, okay, and also for min and second min. Well, it turns out that these two problems behave differently. Okay, for max min, 3/2 n minus 2 is the best we can do. Okay, so 3/2 n comparisons is the best. We need 3/2 n comparisons, while in this case, when for minimum and second minimum, you can do with actually less. Okay, the divide and conquer sort of paradigm gave us 3/2 n, but that's not the best. So why? So let me give you a reason why you can do better here. Okay, to better this, you need to understand a bit more as to how this algorithm works. Okay, let's unfold the recursion out and see what this looks like. Okay, initially I have array elements x1, x2, x3, x4, and so on all the way up to xn. Okay, what we do is we just divide it into two parts, right? We divide it down the middle, and then you recurse on these two. Okay, on the left half we divide it again into two halves, recurse, divide, recurse, divide, recurse. Now we come down all the way down to when the array has size 2. This is when the comparisons start happening. Okay, the recurrence sort of bottoms down till you reach arrays of size 2. Now I'll find the minimum of x1 and x2, and that goes up, right? The minimum of x3 and x4 is pushed up, right? Also the second minimum is pushed up, but let's not worry about that for the minute. In the max min case also it works very similar. You put the max mins are pushed up at each level. Okay, we'll just focus on the minimum element. Okay, so the minimum element is pushed up from here, the minimum element is pushed up from there. At the next level, I'll compare the minimum of these two. Okay, this contains the minimum of x1, x2, this contains the minimum of x3, x4, this contains the minimum of these two, which is actually the minimum of these four, and so on. Okay, this would be a bigger tree, and so on. Okay, all the way up to the root. Okay, at this root the minimum is known, right? So for instance here xn minus 1 and xn are compared, this is the minimum. At the next instance you compare it with the other two. Okay, this would be xn minus 2 and xn minus 3 and so on. Okay, all the way up to the root where the minimum is known. Now this looks like, if n was say a power of 2, this looks like the very familiar complete binary tree. Okay, so there are log n levels, right? There are n leaves, there are log n levels, and at each level you sort of have some sort of minimums on some portions of the array, and these are pushed up. Okay, now where was the minimum element? The minimum element sits somewhere in this array, right? And at each stage it is pushed up. It sort of wins its comparison each time at each level of this tree, and it finds its way to the top. Okay, somewhere it perhaps came from the left, maybe it came from the right, came from the left, and so on. Okay, so it does traverse some route all the way from the root to a leaf, and this is where the minimum element resided. Now what can you say of the second minimum element? Now, well, the crucial sort of observation that you need to make to speeden up the algorithm is that at some stage the second minimum must have been compared with the minimum element. Okay, this is absolutely crucial. If the second minimum element were never compared with the minimum element, then you really don't know which of these two is the minimum, because in each comparison the second minimum one, it was smaller than every other element, right? So was the minimum element. Which of these two is minimum? To know that, you must have compared the second minimum element with the minimum element. Okay, now let's look at this picture. Okay, here's the picture. How many elements did the minimum element win against? How many elements were compared with the minimum element? Okay, if you look at this picture and you follow this, at each stage in this path down from the root to the leaf, the minimum element was compared with exactly one element, right? The length of this path is log n, so the minimum element was compared with at most log n elements in this tree, right? Which means log n elements in this array were compared with the minimum element, and one of these log n elements, remember, must be the second minimum. Okay, so to find the second minimum, all we do is this: find the minimum using this tree. Okay, you can do it recursively if you want. Once you find the minimum element, collect all elements that the minimum element won against, was compared against. Okay, if you have this tree in front of you, you can certainly go down the tree and figure out which were these elements. Among these elements, find out which is the minimum, and that will give you a second minimum. Okay, there are log n elements, so initially you made n comparisons. Okay, maybe it's n minus 1. Okay, n minus 1 comparisons to find the minimum, and then you need about log n minus 1 comparisons more to find the second minimum. Okay, this then is actually optimum, though we will not prove it in this course. There is an argument which shows that you need n plus log n, but it's surprising that you can actually do this in n plus log n, and this problem in this way differs from the previous problem. A straightforward application of divide and conquer doesn't work. You need to use some more intuition. You need to understand the problem a bit more, come up with new ideas. Okay, and that's what algorithm design is all about. Often there are problems which are hard. You really don't know what to do, and when you come up with a smart answer to an algorithm, you feel nice.